Welcome to today's webinar, Determining Lithium Content by the Composition by Difference Method. I want to cover a few housekeeping items before we start. If you have a question, please type it in the questions pane in your console. There's a diagram out of it to the right of the screen. If you have issues regarding connectivity, those questions will be addressed immediately. We'll try to answer all other questions at the end of the presentation, but if we don't get to your question today, we will follow up via email. Now I'd like to introduce today's presenter, David Stowe. David is a senior product manager responsible for energy dispersive spectroscopy products for EDAX and SEM products for Gatan. He joined Gatan in 2007 as an application specialist after graduating with a doctorate in philosophy and a master's in engineering in metallurgy and science of materials from the University of Oxford. In his doctorate and master's research, he used a range of electron beam tools and microscopies to investigate electronic processes in wideband gap materials and to characterize the electrical and optical properties of defects in semiconductors. More recently, he has focused on developing new instrumentation and methodologies to enhance the characterization of materials in the electron microscope. Now over to David.
Hello everyone, and thank you for joining us today for this webinar, where we will be discussing a new method that promises to be of great value in the characterization of lithium-based materials and devices. As you heard, my name is David Stowe. I'm a senior product manager at Gatan and EDAX, and today I'm going to be introducing the composition by difference method, which for the first time has allowed researchers to quantitatively reveal the microscale distribution of lithium in alloy and compound materials such as metal oxides in the scanning electron microscope. I'm sure that you're all very well aware that lithium products have a very significant technological and commercial value, both in energy storage and lightweight structural alloy applications, whether that be lithium-ion batteries or in the aerospace industry. In order to meet the energy reduction commitments that have been made by many governments around the world, improved device performance and wider adoption of these technologies are required. The last 20 years or so has seen really rapid development of these technologies, and however, further work is required and aggressive development roadmaps and investments have been planned for the foreseeable future. Now, electron microscopy is already a key tool for characterization of many of these types of materials and devices, whether that's in research and development, quality control, or inspection. From understanding things like the mechanical degradation mechanisms, packaging failure analysis, to quantifying structure, particles, voids, porosity, tortuosity, to mapping crystallography and chemical composition on a micro or even a nanometer scale, the uses of electron microscopy are wide and varied. However, there is one significant hurdle, and that's an inability to map the lithium distribution in a scanning electron microscope. For example, in lithium-ion batteries, it's not possible to reveal the charge state of cathode or anode materials in the SEM, or to reveal the evolution of structures, including the formation of solid electrolyte interphases, or lithium plating or dendrite growth. Now, typically, we would use a technique called energy dispersive spectroscopy for revealing the elemental distribution of a sample at the microscale. So this is an X-ray fluorescence-based process in the scanning electron microscope. We use the electron beam to generate X-ray fluorescence from a sample, and the energy of the X-ray is characteristic of the atom that produced it. The technique with relatively high sensitivity, and importantly for this talk, can be performed quantitatively. On the left-hand side, here you see an example of an EDS map, actually an overlay of several different elemental maps, including magnesium, lithium, and aluminum. And this is from a magnesium, lithium, aluminum alloy. And the map reveals a eutectic microstructure with submicron feature sizes. However, almost half of the atoms in this sample are lithium, but lithium is not detected at all by EDS analysis. And there are several fundamental reasons why this is the case. Firstly, there's no guarantee that lithium X-rays are actually generated by a sample. In fact, for a wide range of lithium materials, particularly compound materials, the X-ray fluorescence and yield depend on the lithium bonding state, and most don't give out lithium X-rays. In materials where lithium X-rays are generated very few of them actually ever leave the specimen. They're either reabsorbed by contamination or by the sample itself, even before they reach the EDS center. Although some specialized lithium detectors have been developed, they're suitable for analysis, as I said, for a very limited range of materials only, and importantly have a limited detection of about 20 weight percent, so equivalent to about half the atoms in a sample being lithium. Perhaps importantly, and very importantly for this talk, lithium has never been detected by EDS in materials used in the construction of lithium-ion batteries. So commercially important materials, it's just not possible to identify lithium using conventional EDS technique. About 1 year ago, researchers at the Austrian Institute of Technology published a really interesting article which described a brand new method termed the composition by difference method. They used the EDS signal that we spoke about on the previous slides to quantify the non-lithium elements from a region of interest within their sample, or at least those with elements with an atomic number greater than lithium. To this, they added information from a second signal within the SEM that can also be measured quantitatively, the backscattered electron signal. Now, the backscattered electron signal depends on all of the elements that are present in the sample, including lithium, and the difference between these two quantitative signals allowed them to calculate the lithium content. Now, in the magnesium lithium alloys that they analyzed in that publication, they demonstrated an excellent accuracy of about 1 weight percent and a minimum detection limit below 4 weight percent. This was all verified by an external accredited laboratory using an alternative technique. So an incredibly promising first step towards being able to detect lithium quantitatively in the SEM. Now at Gatan and EDX, we are commercializing this process, this composition by difference method, and we're leveraging technology from each of the two companies that you may know and love already, Gatan and EDX. From EDX, we're using the Octane Elite or Elect Super EDS systems, and from Gatan, the on-point backscattered electron detector. And we're combining these with some innovative software to allow us to reveal lithium by the composition by difference method. This is a product that we are in the process of commercializing, and it's a product that will be called Cypher. Now, in late 2021, together with the Austrian Institute of Technology, we published the first quantitative map of lithium in the SEM, this time from a magnesium lithium aluminum alloy, similar to that first publication that demonstrated the concept of the technique. And in that publication, we demonstrated that we're able to map single-digit weight percentages of lithium quantitatively in the SEM. This was a real first. Subsequently, we've been working together with the Austrian Institute of Technology to extend the technique to other materials such as metal oxides that are used in the construction of lithium-ion batteries. Before we look at those results, I just want to discuss quickly the quantitative backscattered electron imaging of compound materials in the scanning electron microscope. So as I'm sure many of you are already aware, backscattered electron imaging is a completely standard technique, imaging technique within the scanning electron microscope. And with this signal, the magnitude of the backscattered electron signal depends on the atomic number or the mean atomic number of the region of interest that's being sampled. So contrast in the backscattered electron image represents a change in the mean atomic number. And in the image you see here, this is a backscattered electron image collected using the on-point detector from a heavy metal polymer composite. So these regions which appear bright are metallic regions, and then the dark regions are polymer. Now the backscattered electron coefficient, or the fraction of electrons that are backscattered, is known to increase with atomic number. It's well described by both Monte Carlo modeling, and there are empirical formulae published in the literature for many years now. However, the backscattered electron signal is not directly proportional to the backscattered electron coefficient. There's an additional gain built into the detectors that we use, as the energy of the backscattered electrons also vary as a function of atomic number. However, under controlled circumstances, you can calibrate the intensity scale of a backscattered electron image by mean atomic number with a calibrated detector. And as a demonstration of this, we collected quantified backscattered electron data from 60 high purity materials of known stoichiometry using the on-point detector, and that's the purple dots that you can see in this chart. These samples included compound semiconductors, oxides, sulfides, minerals, and glasses, and we see an excellent fit of the data points to the trend line. This gives us great optimism that we're able to use this technique to reliably interpret the backscattered electron intensity from a wide range of different materials. Now, the mean atomic number, when measured by backscattered electron imaging, or backscattered electrons, is given by this formula that's available in the literature published by John Donovan several years ago now. What's important to note is that the mean atomic number depends only on the atomic fraction of the elements that are present. So for a region of interest in our sample, we can measure the mean atomic number by quantitative backscattered electron imaging. And we can determine the atomic fraction of elements with, or at least with atomic number greater than 4 by quantitative EDS. By comparing these two different signals, this allows us then to calculate the missing lithium fraction. So I mentioned that we've been working to extend this technique to other material systems, and this is the first proof of principle experiment we did looking at oxide materials. So all of the data that I showed you previously was in metallic alloy systems. This is a lithium aluminate wafer substrate. It's a stoichiometric material with a lithium aluminum oxygen ratio of 1:1:2. So it's a sample that contains 25 atomic percent lithium, or about 10.5 weight percent. As expected, EDS analysis reveals only peaks associated with aluminum and oxygen, and the ratio of aluminum to oxygen is close to the 1:2 that we would expect. Quantitative backscattered electron analysis by the on-point detector shows that the lithium aluminate falls nicely on the trend line, and we can then calculate the lithium content using these two pieces of information. When we do that, we get an atomic percentage of 22.5%, or a weight percentage of about 9.5%. So we are very well, we're within about 1 weight percent again of the lithium content compared to that, that stoichiometric value. So again, a really encouraging accuracy now demonstrated in oxide materials. So we have a nice baseline for these oxide materials, but lithium aluminate isn't a particularly interesting material for many commercial applications. And so we've extended the technique now into materials that are used in the construction of lithium-ion batteries. And particularly the one I'm going to talk about today is looking at lithium, nickel, manganese, cobalt oxides, or NMCs, and these are key materials as cathode materials for lithium-ion batteries. They're forecast to make up almost half of the global demand by different types of battery chemistry within the next couple of years. They're already used in power tools and electrical bikes and other electrical powertrains. They're characterized by this ratio of nickel to manganese to cobalt. There's several different families of these NMC type materials, and the ratio of those, of the nickel, manganese, and cobalt are included within the type of, or within the name of the NMC. So NMC 811, referring to that 8:1:1 ratio of nickel, manganese, and cobalt. Now, in these materials, the lithium fraction actually varies by charge state. So no or very, very low lithium content corresponds to the uncharged state of a battery, and 25 atomic percent corresponds to the fully charged electrical state of the battery. So we have this composition which varies depending on the charge cycle of the battery. Now, the sample that we're going to look at today is an NMC 811 powder, so that ratio of 8 to 1 to 1. And it includes 25 atomic percent, or normally approximately 25 atomic percent lithium, so 7.3 weight percent. And the powder sample that we are going to analyze consists approximately of spherical secondary particles, something like 5 to 30 microns in diameter. These secondary particles are actually agglomerates of smaller primary particles, and we can see that when we look at a crystal orientation map collected using EBSD. So the sample that you see here was embedded in epoxy resin and then cross-sectioned by broad beam argon milling using the Lithium tool from Gatan. The orientation map was collected by the Clarity EBSD detector, and it reveals primary particles 200 nanometers to 2 micron in size, with effectively a random crystal orientation and very few or no gaps between primary particles. So this is the sort of morphology and crystal structure of the samples that we are analyzing. What we're particularly interested in this talk today is the elemental composition of these materials. So obviously the first thing to do is to understand whether we have uniform distribution of the elements that we can identify by EDS. And on the next slide, or on this slide, you can see that within an individual particle, we see little to no variation in the elemental distributions, or at least within the spatial resolution of the technique. So nickel, manganese, and cobalt and oxygen are all detected with effectively uniform composition across the particle. Of course, we can't determine lithium using conventional EDS. Remember that it's important that we understand the distribution of lithium, or the content of lithium within these materials, as that gives us an insight to the electrochemical state, whether the battery is charged or discharged. So for that, we have to go on and use the composition by difference method. So firstly, in that method, we capture a quantitative backscattered electron image, and you see that here on the image on this slide. In this image, every pixel within this image can be related directly to the mean atomic number. We then perform quantitative EDS analysis at selected locations. And doing that, we reveal, unsurprisingly, oxygen, nickel, manganese, and cobalt, as we expect. No other elements were found above the minimum detection limit, and only very limited interparticle variation in composition was observed. That NMC ratio that we've spoken about previously was found to be entirely consistent with the nominal composition, so 8 to 1 to 1. So now that we know the mean atomic number and have identified the atomic fraction of other elements that are present in the sample, we can apply the composition by difference method analysis. And that's shown here using a false colorization to give an indication of the lithium content in each of these particles. So the mean lithium content was determined by this composition by difference method is 22.5 atomic percent, or just under 6 weight percent. So within about 1.5 weight percent of the nominal composition value that was expected. This really is a very significant step forward, as it demonstrates that the composition by difference method can be applied to metal oxide and cathode particles also. We have more work to do in terms of extending this to look at materials of different charge states, with lower lithium content, corresponding to uncharged or partially discharged battery conditions. But we're really excited by the potential that this technique is offering. So as a reminder, this is a technique, this composition by difference technique, which we're commercializing using the product Cypher, is a quantitative way of determining lithium in a sample and also being able to generate spatially varied maps. We've already demonstrated proof of concept in a number of different material systems, including metallic alloys, simple oxides, and then also complex oxides used in cathode materials for battery construction. We use effectively standard analytical tools. They're used in a very innovative way with some innovative software. And it's suitable for bulk samples and compatible with conventional specimen preparation techniques. This does have the possibility to provide you results when the sample's in the microscope in minutes. It's a really exciting step forward, and we really hope that you agree with us that this technique and this product that we are commercializing will really recharge your lithium research. So as a reminder, just remind you all that if you have any questions, to enter them into the to the questions panel in the dialogue on the right-hand side. We'll endeavor to answer as many as you can. I think we have 3 or 4 minutes to answer questions.
All right, first question we have, David, is what is the minimum detection limit?
Yeah, honestly, we're still really discovering what that is. You know, so we've tried this on a number of different material systems, and with pretty good success, I think, in most cases. Within the talk, I think I mentioned already that we've analyzed materials with a few weight % lithium, and I think it's reasonable to expect that we could go below that and push down towards 1 weight %. Ultimately, I think it's going to vary from material to material, and maybe even depend on whether there is a lithium-free analog that would be available to act as a standard. But I think somewhere approaching 1 weight % is a realistic expectation at this point.
Okay, the next question is, the EDS and backscattered electron signals originate from different volumes within the sample. How do you ensure that they're sampling the same region of the sample?
That's an important question, and something I didn't really speak to in this webinar today. In order to use this method, it's really important to ensure that the signals that you're comparing originate from the same volume of your sample. So it means that the analysis that we do is actually performed sequentially at different accelerating voltages. So the different accelerating voltages give a different penetration of the electrons within the sample, and we attempt to align those 2 different conditions for the 2 different types of signal. So normally we would need some knowledge of the specimen in order to be able to apply the technique, either based on what we expect to be in your sample, or to use some kind of pre-characterization using EDS. That then allows us to perform Monte Carlo modeling to really select appropriate conditions to carry out the sequentially captured data. And actually, that's one of the important things about the software that we're developing to do this, is to ensure that you have proper registration between the data analysis points for the 2 different signals. So when changing the accelerating voltage, the magnification and image rotation, and a number of other different things change within the electron microscope. So that's something that the software we're developing for CIPHER will allow users to really eliminate that kind of disparity between the information from the 2 sequentially captured data sets. So yeah, I hope that answers the question.
Okay. Does the backscatter signal depend on other factors such as topography, crystal orientation, and sample density?
Yeah, so topography is certainly an important consideration. Both EDS and backscattered electron imaging require flat samples, or at least for quantitative analysis of those signals. However, in the tests that we've done, both conventional mechanical polishing and broad beam argon milling using something like the PEX or the Ilion tools from Gatan appear to be entirely suitable ways of preparing specimens. I don't know whether you saw, but in some of the maps that I showed earlier, there were areas which we didn't show lithium content, and they were regions where there was significant topography on the sample. Some of the other things that you need to consider is also sample charging. So charging is important to control. That can change the energy of the landing energy of the electrons, causing uncertainty or and reliability in the quantitative analysis, both the EDS and the BSE signal. Was it crystal orientation was the other question?
Yes.
Yeah, so crystal orientation is much less of a concern. So for the detector geometry that we use and the kind of analysis conditions, things like channeling contrast have very low overall contribution to the signals that you measure. So as an example, we ran a test looking at a lithium fluoride powder. So small, few micron sized lithium fluoride particles dispersed in an epoxy resin and sectioned. And so we were able to look at several hundred particles at effectively random orientations, and there was next to no interparticle variation in the backscattered electron signal, for example. So I think that crystal orientation, and by selecting the right conditions and having the detector geometry right, things like sort of channeling contrast and crystal orientation, you can effectively eliminate from the as a concern in the analysis.
Okay. Have you tried the technique with anode materials such as graphite anodes?
No, not yet. So we've done some further tests, or we have other tests in progress and have used the technique on some other cathode materials. I mean, so we looked at lithium iron phosphate, for example, but we haven't extended it to anode materials yet. And we're hoping that we have plenty of customers who will look to push into that direction for us.
Okay. One audience member is asking, can I send a sample for a demo?
I like that question. At least the talk was interesting to somebody out there. I think the best approach for that would be to make sure that you're in contact with your local sales representative, and then we can discuss a pathway forward. If you don't know who that is, I guess you could enter your details into the chat window here, or send up a follow-up email to what's being sent out. But as we're still developing the commercial product for this cipher, we don't have everything ready to accept all requests for demos yet, but that's something that we can definitely discuss later on a one-to-one basis.
Okay, I think that's all the questions we have time for today. We will answer anything that we haven't gotten to via email. David, I'd like to thank you for the presentation. I'd like to thank everyone for attending. The recording of the webinar will be available within a week. It'll be available on both Gatan.com and edax.com. Thank you all for your time.
Thank you, everyone.